Welcome. In the last lecture of the infinite series, so we have to study there what is the geometric series and what is the convergence of the geometric series. Okay, let so summation rs to n is a geometric series. Then if r is less than 1, then the series converges, and if r greater than equal to 1, then series diverges. So this is the theorem. We have to prove that theorem in the last lecture. In this lecture, we take an example. Test the convergence of the series, following series. So 1 by 5u plus 1 upon 2 upon 15 plus 4 upon 15 plus 8 upon 135u, 8 upon 135u, 45 here, plus and so on. So this is the series given here. So find the convergence of that series. Test the series here. Okay. So the given series can be written as 1 upon 5u plus 2 upon 15 plus 4 upon 45 plus 8 upon 135 plus and so on. So this series can be written in the form. So we common out 1 by 5u from this series. So in the bracket, so that is 1 plus 2 upon 3 plus 4 upon, so I think this 2 raised to 2, that is 4 is 2 raised to 2 divided by 5 common out, 15 is there and 9 is there, so that is 3 square plus what happened here, 8, that is 2 cube divided by, so 5 common out, so remaining there 3 cube, so that is 27 plus 5, that is 135u plus and so on. So this series becomes like that. So what is the nth term of the series? The nth term of the series is nth term of the series. So what happens? So what is the series here? So an, something un is equal to. So that is what happened here. So that is 1 by 5 as it is. And what is the nth term? So that is 2 raised to n divided by 2 raised to n minus 1, I think. N minus 1 divided by 3 raised to n minus 1. So this is the nth term of the series here. Nth term of the series. So this is first, second, third, fourth. So that is 4 minus 1. 4 minus 1. So what is nth term? So 1 upon 5 into 2 raised to n minus 1 divided by 3 raised to n minus 1. So this can be written as 1 by 5u into 2 by 3 raised to n minus 1. So this is un here. So nth term of the series here. So what happened? So this is the series with common ratio. So the series 1. The series 1. Series 1 is geometric series, with common ratio. What? Common ratio r is equal to 2 by 3. R is equal to 2 by 3. Okay, so this is very simple here. So this is a geometric series with common ratio. So this divided by this is a 2 by 3. So ratio of two consecutive terms. So that is a 2 by 3. And this is a constant throughout. So it is called common ratio. So but if r is equal to 2 by 3, So r is equal to 2 by 3, r. So 2 by 3 is less than 1. 2 by 3 is less than 1. So that is r is less than 1. Then the series converges. Then the given series is convergent. Okay. So find out the limit of that series here. So that is again. So we decide here. So this series is convergent or divergent. We decide here the series is convergent here. So again, we find limit. Again, Sn is equal to. So what is Sn? So nth term of that series. So nth term. So that is 1 by 5u. So this is first term plus 2 by 3 plus this is a 2 by 3 raised to 2 and so on. What happened? So what is the nth term? 2 by 3 raised to n minus 1. Okay. N minus 1. So this is a partial sum. Means sum of n terms in this series. So this is Sn we say here. Partial sum. So what happened? So this is 1 up by 5u. Then what is the sum of partial sum? So this is 1 minus 2 by 3 raised to n divided by 1 minus 2 by 3. Okay. 2 by 3. So what happened here? So this is what? So this can be written as, so limit, so 1 minus 2 by 3, so that is 3. 3 minus 2, 1 by 3, so this is 3 by 5. 3 by 5, okay. So this is 1 minus 2 by 3 is what here? 2 by 3, so 2 by 3 raised to n, okay, this term, okay. So taking limit of Sn as n tends to infinity is equal to 3 by 5u. Limit 1 minus 2 by 3 raised to n. So what is the limit of this as n tends to infinity? So this is a 3 by 5u. 3 by 5u into bracket. So limit of this is 1 and 2 by 3 is less than 1 raised to n and n tends to infinity. So this is 0 here. Less than 1, 2 by 3 and raised to n and n tends to infinity. So this is 0. So this is 3 by 5. Therefore, sequence Sn converges to what? 3 by 5. Therefore, the given series, by definition, the given series converges to 3 by 5. Hence the example. So we solve this example by using geometric series here. Okay, geometric series. If r is less than 1, then the series is convergence. If r greater than equal to 1, then series is a divergence. So now, what is the comparison test of positive series? So that is comparison test 1 here. So we study here. What is the comparison test 1? Comparison test 1. Okay, so what is the statement of comparison test 1? So let statement, let summation un and summation vn be two positive series B2 positive series means each term of the series is positive, greater than 0. By definition, positive series such that un is less than equal to vn. Un is less than equal to vn if for all n is equal to 1, 2, 3 and so on. Means each term, the corresponding term of un is less than equal to corresponding term of this series vn. Okay, then one, if the series vn converges so it implies that then summation, so that is un also converges. And what is the second? If un, series un diverges, then the series vn also diverges. So this is a comparison test 1 here. So what is the statement here? Let un, summation un and summation vn be two positive series, and if un is less than equal to vn for all n is equal to 1, 2, 3 and so on, then if this series summation vn, so this vn series converges, then un also converges. And second is what here? So if the series un diverges, then series vn also diverges. So we take an example. What is the example? So prove that the series, very important example, summation n is equal to 1 to infinity 1 upon n diverges. Very important example. So we solve this example by using the comparison test to 1 here. So solution. So we consider the series 1 upon n that is given here. So this is put n is equal to 1, 2, 3 and so on. So 1, put n is equal to 1 half, n is equal to 3, 1 third, 1 by 4 plus 1 by 5u and so on. So this is the series here. So we write this series in the form 1 plus 1 half plus 1 third into bracket 1 half plus 1 third and 1 by 4 in bracket 1 by 5u plus 1 by 6 plus 1 by 7 plus and so on. So we collect 2 terms here, then we collect 4 terms here, then we collect 8 terms, then 16, 32 and so on. So we write this series in this form here. So this is equation number 1. We consider another series. Consider the series. So what happens is 1 plus 1 half plus 1 by 4 plus 1 by 4 plus 1 by 8 1 by 8 1 by 8 1 by 8 plus and so on. So 1 by 4 1 by 4 2 times, 1 by 8 4 times, then 1 by 16 8 times and so on. This is 2. Okay. So now we compare both series. So use consider here. So this is un series and this is another vn series here. Un and vn. We consider that series. We say that is a vn series. So this is un series. Okay. So each bracket of series 1 of 1 is greater than corresponding bracket of corresponding bracket of 2. Okay. So each bracket of 1. So this bracket is greater than this bracket. This bracket is greater than this bracket. Okay. So now series. Series 2. So what is series 2? Implies that. So what happened here? 1 plus 1 half plus. So 1 by 4, 1 by 4. So that is 2 by 4. Then 1 by 8, 1 by 8, 1 by 8, 1 by 8. So then 4 times 1 by 8. So that is 4 by 8. Plus and so on. So this is equal to 1 plus 1 half plus 1 half plus 1 half plus and so on. Okay. So this can be written as 1 plus 1 half plus 1 half. So 1 half plus 1 half, write this bracket. So 1 half, next 1 half, plus and so on. So this is what? So 1 plus 1 half plus 1 half, 1 plus 1 half plus 1 half, 1 plus and so on up to infinity. So what is this? So clearly the series 2 is a divergent. Clearly. Series 2 is divergent. Ranka, this 1 plus 1 plus 1 plus 1 plus 1 plus 1 and so on up to infinity. So that is infinity. Therefore, the series 2 is divergent. Okay. So we consider this is a series. What happened here? The series is something Vn. Okay. Then by comparison test. Okay. Then by comparison test. So one series is convergent, then other converges. So the one series diverges, then other diverges. Okay. Then by comparison test. Then by comparison test. By using this statement, comparison test. Test 1, the given series is divergent. The given series is divergent. Okay. So this is an important example. So we use this example. So what is convergence of this? So that is series divergence in many theorems or any and other examples. So this is important examples. Okay. So now we take care. What is the P series? What is the P series? P series. What is the P series? So definition is very simple here. Okay. So the series in the form, a series of the form summation 1 upon n raised to p, where p is greater than 0, is called P series. Very simple, is called P series. Summation 1 upon n raised to p, where p greater than 0, then this series is called P series here. So what is the convergence of that series also? Okay, so what is the theorem here? Theorem. What is the convergence? So you know what is the P series, then what is the convergence of that series is the theorem here. The P series 1 upon n raised to p converges if p greater than 1. P greater than 1. Okay? And diverges if p less than 1. Okay? So show that the p series converges if p, value of p is greater than 1, and diverges if p is less than 1. Okay? Proof is very simple. Okay? Case 1. So what is case 1? If we take p is equal to 1 here, p is equal to 1, then what happens? P is equal to 1, then the series becomes 1 upon n raised to p, the p series. So this becomes 1 upon n. Put p is equal to 1. Then p is equal to 1. Then the series becomes here 1 upon n. So what is this series? Is it convergent or divergent? Just previous example, we show that the series is divergent. Therefore, in this case, the series, so in this case, just we take the example and prove that the series is divergent. Okay, this series, in this case, the p series, summation 1 upon n raised to p is divergent. Okay, just we prove divergent. So next case 2. So what is the case 2? So if p is less than 1, p is less than 1. So this p is less than 1, then what happens? Then the series becomes here summation 1 upon n raised to p. So what happened? So this series is 1 upon 1. So put p is equal to something 0. So this is n raised to p, p is equal to 0. 0. So then what happened? 1 plus 1 upon, just what happened here? So put n is equal to 1 to infinity. Put n is equal to 1. So 1 raised to anything. So that is 1. 1 upon 1, 1. So put n is equal to 2. So 2 raised to p. Put n is equal to 3. 1 upon 3 raised to p. Plus 1 upon 4 raised to p. And so on. Okay? So this is the p series here. So then, the series can be written as 1 plus. We write this two terms, second two terms here in bracket. So 1 upon 3 raised to p plus 1 upon 4 raised to p plus 1 upon 5 raised to p plus 1 upon 6 raised to p plus 1 upon 7 raised to p plus and so on. Okay? Plus and so on. So, this is a less than. This is less than what? 1 plus 1 upon 2 raised to p plus 1 upon 2 raised to p. Okay? Okay. Plus, so this bracket is less than this. Okay? So this is less than 1 upon 4 raised to p plus 1 upon 4 raised to p plus 1 upon 4 raised to p 4 times here plus 1 upon 4 raised to p and so on. Okay? So this series, this means this, and this series is less than this series because this bracket is less than this bracket is less than this, and so on. So this series is less than this series. Okay? It's so very simple here. So okay, so this is equal to 1 plus. So this plus this is a 2 upon 2 raised to p plus 4 times. So 4 upon 4 raised to p plus 8 upon 8 raised to p plus and so on. So okay, and so on. Okay. So this is a very simple one. So if P, I think just to P greater than 1 here. So we P greater than equal to 1. So this is the series here, P greater than equal to 1. So what happened here? So this is 1 plus 1 upon 2 raised to P minus 1 plus 1 upon 2 raised to 2 into bracket P minus 1 plus 1 upon, so this can be written as, so this is very simple, 3 P minus 1 and so on. Okay, but this is a geometric series with common ratio. R is equal to 1 upon 2 raised to P minus 1. So this is geometric series with common ratio. R is equal to 1 upon 2 raised to P minus 1. Okay, but we know that if this is less than 1, and if P is greater than 1, if geometric ratio is less than 1, then the series is convergent. Therefore, the given series is convergent. Okay, so we prove the case 2 here. So we prove for P is equal to 1. We prove for P greater than equal to 1, Okay, now we prove the same theorem. What is the case 3? So case 3 is what? Case 3 is what here? P less than 1. So already we prove the theorem for P is equal to 1. Okay, so this is a divergent, and for P greater than 1, then the series is convergent. Then what happened for P less than 1? So if P less than 1, then 1 upon n raised to P is what? So what is the relation between 1 upon n? If P is less than 1, so the denominator become less than this, so this is a less than 1. Okay, so but the series what happened? Summation 1 upon n. So we take summation here, summation. So this is summation. So this is un, vn. Okay, so this is a divergent, but the series is a divergent series. Okay. If this is a divergent series, this is Vn and this is Un. So then by comparison test, if this is a divergent series, then the series, this is a divergent series, then the series 1 upon n raised to P is also divergent series. Okay, hence the proof here. So we prove here, so the series P series is convergent if P greater than 1 and divergent if P is equal to 1 and P strictly less than 1. Hence we prove here and we stop here. We shall take example in the next lecture. Thank you.